First of all, I would like to thank you for joining me today at this what we call as pivotal moment, right, where science fiction transcends into science fact. So what was science fiction maybe 5, 10 years back is turning out to be a science fact, right? So today we will deep dive into intricate world of machine learning and artificial intelligence, not just as a bystander, but as an active participant shaping the future of this transformative journey. So let's begin. Okay, there are a few topics which I want to cover for next about 100 minutes or so. We'll explore advanced techniques and latest breakthroughs that continue to challenge and expand our understanding of what machines are capable of achieving. From the depths of deep learning into the cutting edge developments in AI that are redefining industries, we will cover the terrain of this vast and dynamic field. Okay, so let's embark on this journey together. So I've divided this presentation into three parts. First, we'll talk about advanced machine learning techniques. Then we'll get into the generative AI. That's the current trend in AI. And then we will wrap up with some thought-provoking discussions. So let's get started with the first topic I want to talk about today is convolutional neural network, or what we call as CNN in short, right? So the primary use of CNN, okay, is it's a class of deep learning models primarily used for processing data with a grid-like topology, right? So this grid-like structure is most commonly found in your images where pixels are arranged in 2D grid. CNNs can also be applied to other types of data, such as your time series data, which is like one-dimensional grid, or your volumetric data, which could run into three-dimensional grids, right? So how does CNN work? The core operation in a CNN algorithm is the convolutional, where a small filter, or what we call as kernel, is applied across the input data to detect patterns. In the context of image processing, these filters are typically small, maybe 5 by 5 pixels, and are convolved across the image to produce a feature map. Now, each filter is designed to detect a special pattern or features such as like edges, textures, could be simple shapes. So in the initial layers of CNN, here on the down image, okay, yeah. So in the initial layers of the CNN algorithm, the filters are designed to capture low-level features like edges, corners, and textures. And as the network goes deeper, the layers are able to capture more complex patterns by combining these low-level features. This hierarchical feature extraction allows CNNs to recognize increasingly abstract representations such as shapes, objects, and even entire scenes in an image. So these layers are used to reduce the spatial dimensions of the feature maps, which helps to decrease the computational complexity and reduce the risk of, let's say, overfitting. The most common type of pooling is, the max pooling, where the maximum value in a specific window, which could be like generally 2 by 2 window of the feature map is selected and thereby downsampling the image. So now if you talk about the examples where CNNs are used, you have image recognition, and this is of course the most common application of CNN. Then you have object detection. So CNNs are also used in your object detection task where the model identifies and locates objects within an image. So for example, in autonomous driving, CNNs can be used to detect pedestrians, vehicles, and road signs. Okay, when we talk about medical imaging, CNNs are applied in medical imaging to identify anomalies such as tumors in X-ray, MRIs, or CT scans. The network can learn to recognize patterns associated with different types of tissues and abnormalities. So this is about CNN, convolutional neural network. And the next algorithm I'm going to talk about is your recurrent neural network. Now, still before generative AI was used, we mostly used RNN to generate text. No, it can't generate text in paragraphs or pages like what ChatGPT or other generative AI algorithms can use, but definitely it can predict text. And if you talk about using Google search like 10, 15 years back, this was the algorithm behind those search engines. So your RNN are specially designed to handle sequential data, okay, making them particularly well suited for tasks where the order of data point is crucial. So if you talk about, so I was talking about, RNN, and when you talk about different variants of RNN, LSTM is another a very popular deep learning algorithm, neural network algorithm. So it's a kind of RNN, okay, and it can handle even longer, long-term dependencies, right? It can, handle multiple previous steps well analysis. Then you also have gated recurrent unit or GRU. It's a simpler alternative to LSTM, okay, that also addresses your vanishing gradient problem. So there are different forms of RNNs which tries to do things better, but nothing can beat the transformers. Okay, and the transformer is something that is currently everybody's talking about. Okay, and in my presentation today also, we will be visiting this transformer 2 more times. So I'm going to talk about this 3 times, okay, and every time with some kind of input. So here we're just introducing this concept, okay, and this transformer concept was introduced by Vaswani and others in 2017. And when they wrote a paper, they were working in Google, right? So they are all Google scientists. They come out with this paper called as "Attention is All You Need." Okay. Now, generating text, for example. Now, of course, it can be used for multiple things, but mostly it's been designed to handle text. And initially, it was uh, designed to perform our language, natural language translation, translating text from one form to another. And that's why, so this paper talks about things that fall under our NLP topic. Now, transformers, okay, allows for parallel processing, okay, so making them highly efficient and effective, of course. And, the one thing that makes transformer different than others is the self-attention mechanism. Okay, so the self-attention mechanism enables the model to focus on different parts of the input data based on their relevance to the task at hand. Okay, so now to simply put it, if I say here, okay, sky is, okay, now the sky is the given text, what would come, okay, after that? So there are multiple things that come, right? Sky is red, sky is blue, sky is black, sky is falling, right? But it tries to figure out words, okay, and it tries to, once it puts the word, it tries to calculate the attention, right, or the value which best suited. For example, on the right side, I have given example here, right? Let's say you have a input example called the quick brown fox. Now, quick brown fox can do, there can be multiple words, but based on the training, it figured out that jumps is the best possible word that comes there, right? So jumps comes here. Now, when you put jumps, okay, then what should be the next best possible word? Okay, so the attention is, that's what we're saying. Okay, we are not only looking at the words, but also position matters. And of course, when you change the position, word also changes, right? So this was the theme of that paper. And the self-attention mechanism, allows the model to weigh the importance of different words. Of course, like, machine learning algorithms or AI algorithms cannot handle words, text, right? It has to handle data in tokens. So we have to convert the input text into embeddings and things like that, which is required before you perform transformer. And we call them as tokens, right? So the importance of each token in a sequence, okay, is captured regardless of their position. Okay, and that is very much important when you form a sentence. Now, okay, now let's say we all know at least 2 languages, right? So when you try to translate a text from one language to another, the words doesn't like, it's not simple word to word translation, right? When you try to translate a sentence, it's not simply word to word translation. So one thing is, yes, let's say you have a sentence in English and we want to translate it into maybe Telugu or Hindi, whatever. So when you translate, of course, first we translate the word and then we have to find the right place, right? So the word which might fall last in English, the translated word might fall in the beginning itself of the translated text. So the translation, okay, and the concept that we talk about transformer is easy when you talk about the translation thing, but it applies to all the concepts. When you're generating a say essay, okay, now we start with certain word. What word should come next, right? Also matters here, right? So that's the purpose of your the transformer. Transformer decides the importance of each word at a given place. So each word in the input sequence is represented as a vector, right, after embedding. And the self-attention mechanism operates by comparing each word to every other word in the sequence to determine their relationship. Okay. And the one which shows stronger relationship is where the word will come and fit, right? So if I have to translate something like I am going into Hindi, right? Now, when you translate it, okay, you will get the three equivalent word. But where, so each of these three words are compared. Okay, which word should come first and which word should come second. So when you compare, there's a scoring mechanism that is given. Okay, so every word with every other word, there will be a scoring mechanism, and the score, the combination which has the highest score is what is printed as output. Okay, so that's the job of transformer, and we'll come back to it again later sometime when we talk about when we move to our third module, which is second module today. Okay, that which is about generative AI. So those are the three algorithms I want to talk about: CNN, RNN, and introduction to transformer. Now, there are other important concepts in machine learning like boosting and backing. We call them as ensemble methods. So ensemble methods are designed to improve the accuracy of a single model, right? So we would have done different models. There are a lot of models that we are there, but can we improve the accuracy of each model? So what we say, right? When you combine more than one algorithms together, models together, it should perform better than each individual model, right? So there are different ways of putting algorithms together, and that's what we'll talk about for next few minutes. So the first model that we'll talk about is called boosting and bagging. Okay. So your boosting and bagging are ensemble learning techniques. Okay. Ensemble is where you are, not using just one model, but more than one model. Okay. So to improve the performance of machine learning models by combining multiple weaker models. Okay. So weaker models are often called as weak learners. Okay. You can also refer to them as weak learners. So we combine these multiple weak learners or weaker models into a single robust prediction model, obviously, to improve the accuracy of the model, overall model, right? Overall accuracy of the model. So both techniques, okay, boosting and bagging, are aim to enhance the accuracy and generalization of models, but they have a different approach, okay, and that's what we're going to talk about. So if talking about, let's say, bagging, okay, it is also called as bootstrap aggregating. So bagging aims to reduce the variance of a model by creating multiple versions of a model, each trained on a different subset of the data. Okay, so you can, in the graph, you can see, there are three parallel algorithms that are running. Okay, so there's a model running on each subset of the data. Okay, and okay, and then what we do is at the end we average, okay, the overall the output of this models is average, and that's why it's able to give more accurate result than just a single model. Okay, so bagging starts by creating multiple subsets, as you said, of the training data. And the concept that we use for doing this is bootstrap sampling. Okay, so using bootstrap sampling technique, we create samples of the main data. where each subset is generated by randomly selecting samples from the original data set, okay, and with replacement. So that means that when it creates second data set, it could include the data set from the first data set as well, right? So with replacement, we create samples. And then we select, we train using a weak learner, right? Mostly we use decision tree in this case. So decision trees are applied on each subset independently, okay? And because of the subset differ slightly from each other, each model might learn different patterns, obviously, correct? So once all models are trained, their predictions are combined. So for regression task, this typically involves averaging the predictions. For classification task, it usually involves voting, right? So the majority vote. So if a certain particular input is classified as, let's say, yes by 70% of the model and 30% says no, obviously we go with yes because majority of the vote is for yes. Okay, so this result in a final model that is more stable and less prone to overfitting than any individual model. Okay, so each model in the ensemble training in case of bagging is trained independently and in parallel. Okay, so they work in parallel here. So random forest is one example of bagging. So random forest is a popular example of bagging algorithm, which is again based on decision trees, right? Now, if you talk about boosting, okay, so the boosting aim is also to reduce bias, okay, and improve models accuracy by sequentially building a strong model. That means, okay, you have a model and the output of that model is not the final output that we look at. Okay, that is given as input to the next model. Similarly, input to the next model, output of the next model is given as input to the third model. Okay. So again, to tell you, explain it in a general way. Okay. Let's say, assignments are given to a student. Okay. Mathematical problem is given to a student. Okay. And let's say, in case of bagging, all the students, what they'll do, let's say there's a group of 5 students, what they'll do is five of them will solve the problem independently. And then when they look at the answer, they'll say, oh, these answers are different. Oh, answers are different. Let's do average. They will average the answer and that will be given as the final answer. This is typically how bagging algorithms work. Boosting is, let's say, what happens, in the same 5 students, the first student will solve the problem and say, okay, see, I've done this 10 steps. I'm sure about first 2 steps, but I'm not sure about third step. You just have a look. Second student will review all the steps, but since you have said that you are sure about step 1 and step 2, the student will not focus much on step 1 and 2. Of course, it's not going to ignore it. Okay, it's going to review step 1 and step 2, but it's not going to focus on step 1 and 2, but focus on other steps. And then that second student will pass on the same problem, okay, to the third student saying, okay, the first one said 1 and 2 step he's sure of. I am sure about 6th and 7th step, but I'm not sure of other steps. Third student will again go through entire problem, okay, giving less importance to those 4 steps, giving more importance to other steps, which still they have not figured out. And after end of this 5th student, whatever answer comes is submitted as solution, right? That's how, the boosting work. Okay. So the after first model is trained, its errors are analyzed and more weight is given to the misclassified, the error input. Okay. Because, okay, when, the error inputs is what you have not been able to classify correctly, isn't it? So more weights are given to the misclassified instances or the rows of the data. So after each model is trained, observation that were, misclassified, okay, or wrongly or poorly predicted are assigned higher weight. So the next model focuses more on those difficult cases. Okay. So this process continues for a predefined number of iteration, like 5. I just give an example of 5, but it could be 500, 1000 generally we do. And the final prediction is a weighted sum of the prediction from all the models, right? With more accurate models typically given more weight. So what you get end of this is their final output. So boosting is particularly effective at reducing bias in a weak learners. Okay, so which of course lead to better performance of a complex task. It's like 5 models working on one single complex task. So definitely it's going to give you a better result and less bias. So Adapt Boost, okay, adaptive boosting or Adapt Boost is again the popular example of ensemble method that follows boosting concept. Okay, so each iteration, the algorithm increases the weights of the misclassified instances. That's typically how boosting works. Then you also have gradient boosting. Okay, so gradient boosting is another example where new model is trained to predict the residual error of the previous model, right? So again, bagging and boosting we are done. Then there's one more model, okay, which is again ensemble method. It's called stacking. Okay. Now, stacking is again advanced ensemble learning technique that combines your multiple classification or regression models. Now, the main difference between this one and the other two models that we did bagging and boosting earlier was that in bagging and boosting, okay, we talk about um, uh, uh, what you call as meta model. Okay, so meta model is typically a weak learner, but in this case, okay, each of these model could be a strong model. Okay, it need not be weak model or it could be multiple models. Okay, or strong models. It could be like one could be SVM, one could be your logistic regression. Second thing could be decision tree. Okay, so there is no limit on which type of model we select here. So, the multiple base model, right? Which we call as we call as level 0. So first, when all these base models are trained, we call them as level 1 models. So these are trained on the complete training data set. Remember there, what we had was portion of data set, and data set would change in bagging. It's a subset, right? In boosting, okay, it's not subset, but every iteration the data set changes because we are giving more importance to the data which is wrongly classified, correct? But here, okay, it's like running 3 different algorithms. So you give entire data set, okay, to all the base models or level 0 models, okay, and each base model here attempts to make prediction on the training data independently of the others. Okay, so once the base models are trained, they are used to make predictions on the training set. These predictions serves as a new feature for the next steps. You see the green box here. Okay, so this is coming from all the 3 different models. So the meta model is created here, which we also call as level 1 model. So this level 1 model is then trained using the predictions of the base models as input features. Okay. So the target variable for the meta model is same as the original target variable from the training set. Okay, so that model, the target doesn't change. The meta model learns to weigh the predictions from the base models to make a final prediction. So it essentially learns which base models are more reliable under what conditions. Of course, these are trained on training data, so you can actually look at the accuracy of each of these individual models. So during the prediction phase, each base model makes predictions on the test data, and these predictions are passed to the meta model. So the meta model then combines these predictions to generate the final output. So we're talking about level 0, level 1 models, right? Um, so talking about example, okay, so let's say you have a, we'll start with classification problem. Let's say you have a classification task and we use, let's say, a decision tree, logistic regression, and let's say KNN nearest, K nearest neighbor, right? KNN classification, right? So in classification, our objective is to predict numerical value, right? Or the probabilities, okay? So we take, let's say, logistic regression, KNN, and let's say decision tree. So after training these 3 different models, okay, level 0 models, we use them to predict the probabilities of the positive class on the training data. Okay, so each of them is going to give their own prediction. So these probabilities become the input feature for our meta model or your level 1 model. which could be a simple logistic regression model because it has given us better accuracy than other two. So the meta model learns to combine the strength of decision tree, logistic regression, and KNN to make the final classification. Okay. Okay, and similarly, we can use it for regression or classification. Okay, so this is how stacking, which is also an ensemble method, but works different than our let's say bagging or boosting algorithm. Okay, next we have something called as reinforcement learning. Okay, um, so your reinforcement learning is a branch of machine learning, obviously, where an agent learns to make decisions by interacting with an environment. Okay, so the agent's goal is to maximize cumulative rewards over time, which is which is achieved, by taking actions that influence the state of the environment. Okay, so the agent learns from the consequences of its actions through a trial and error process. Okay, so receiving feedback in the form of either rewards or penalties. So higher the reward means the agent should do more often. And when you get penalty, it tells model that there is a risk involved in doing this. So do less of that. Okay, so penalty will tell do less of that. So if we talk about the key components that we generally talk about in reinforcement learning, and also it is presented in the figure that is shown on the right. So we talk about agent. So agent is the decision maker. Okay, it learns. Okay, it tells the model what should be the next step. Okay, so it is the decision maker which interacts with the environment. So now you have environment. So environment is an external system with which the agent interacts. Environment is typically modeled as a Markov decision process. Okay, so there's a Markov decision. So what does Markov decision talks about? In Markov decision, we talk about the next step or the next stage based on your current step. So for example, if I want to predict whether it's going to rain tomorrow or not, so for that I need to know the weather now, right? And then I can predict, okay, it's cloudy, so maybe it will rain. It is too hot and rainy season, it's going to rain. Okay, it's bright, too bright, sunny, maybe it will not rain. So whether it's going to rain tomorrow or not, okay, is dependent on more of the situation today than what was last week, right? So the weather, what was the weather like last week will not or will probably have very less impact on the weather that's going to happen tomorrow, right? So your current state decides your future state, okay? Not what state you were in 2 days back. So that's where environment are generally modeled as a Markov decision process. And then we talk about state. Okay, so state is a representation of the current situation of the environment, right? So state provides all the information necessary to make a decision. Then you have action. So action is a set of all possible moves or decisions the agent can make now. Okay, and then you have a reward, generally represented as R. So your reward is a feedback from the environment. Okay. Okay. So environment has different state, and those different states is dependent on your current state, and agent will take an action. Okay. Action is A, and this action is based on risk and reward, right? So reward is like feedback from the environment. Okay. After the agent takes an action. So rewards can be positive, what you call desired outcome, or negative, which is undesired outcomes. Now again, to talk with a normal example, and then we'll come back to machine learning example. Let's say you are riding on your car. Okay, you're driving your car, and then you see a signal there, and the signal is red. So environment is the signal. Okay, red is the state. Okay, that means the signal is in red state. Okay, you are you are driving the car, so you are the agent. Okay. Now what will be your action? Okay. So your action, okay, is let me go, let me not stop, or you will stop. Right. So here, which is the positive outcome? Stopping is the positive outcome. Right. So if you stop, okay, the thing is going to happen, or maybe you are going to get delayed by, let's say, of 2 minutes to your destination. So that's the negative reward. Let's say you're delayed by 2. But if you had not stopped, okay, you could result into accident. Okay, you could be involved in accident, or you could be paying or right fines. Okay, so what happens? Not stopping has a much more undesired outcome than stopping. Okay, so the reward for stopping is more than, okay, for not stopping. So your reward will decide your action. Okay, I should stop. Again, we talk about driverless car, autonomous vehicles. That's the decision they're going to make. Okay, now when you are in front of steering, now you would have gone to driving school to learn car, right? Your trainer would have told you a few things. But now when you are on your own driving the vehicle, the decisions that you make is your own decision. Okay. There is no rule book saying that you should be going at speed of 40, then you should, so every action that you're deciding is on your own, not a if else condition, right? So that's what AVs will not be designed on if else conditions, on your current state, future state. Okay, what action will decide, how much risk and reward will be there. Based on that, decisions will be taken by the autonomous vehicles. We also have something called as policy as another keyword here. So policy is the strategy or a mapping from states to actions. If I do this state, this is, if this is state, okay, and if I move to this state by taking this action, then how much is the so here in policy, we only talk about different state. Okay, you are in, you are in, you are at a crossroad. Okay, you could, your action could be stop or not stop, right? These are two policy that you have. The last one is value function. That decides the value that each policy or each steps in the policy, okay, will get. So function that defines estimated, or what you call as, the function that estimates the expected, okay, cumulative reward. So here also stopping, probably, there is a, there's a problem that you'll be delayed by 2 minutes. Okay. But if you talk about the cumulated reward, okay, it is still less negative than getting involved in accidents or paying fine of 1,000 rupees, right? So value proposition, okay, is created, okay, based on particular state. Uh, um, okay, so better, how do I put it? State action pair. Okay, so every state and every action that you take in that state. So every state action pair, you will have a value that is created. Okay, and your best action is determined by the reward. Okay, so you have multiple state action pair. Okay, but the one that decides your output is the one that has the highest reward, right? So, okay, so this is again family of algorithms, just like we have regression and classification. Now, if you talk about specific algorithms within reinforcement learning, these days we talk about deep Q network, okay, DQN, deep Q networks. So your deep Q networks, okay, was introduced by, a company called DeepMind. And some of you have been tracking AI for a few years. You remember this company, DeepMind. They developed chess games and various other games, okay, where the players actually competed with this one. So DeepQ network was designed in 2015 by your DeepMind, and it combined Q learning with deep neural networks, okay, where your reinforcement learning agents, okay, learn directly from the high dimensional sensory inputs, okay, which could be your image, which is like a multi-dimensional, okay, it could be a high dimensional matrix kind of thing, which could be your images. You also have something called as AlphaGo. So AlphaGo was also developed by DeepMind, Okay, and uh, okay, and there's a game called Go. Okay, and it defeated world champion Go in 2016. Okay, Go is a complex board game similar to chess, but even more. It is considered even more complex than chess. Okay, so your AlphaGo actually combined the reinforcement learning with Monte Carlo tree search. Okay, so Monte Carlo it decides multiple state action pair, and which at every situation you have multiple. It's like a tree, complex tree, right? So which tree gives you highest reward? Okay, and deep neural networks, of course. So AlphaGo was designed in 2016, which is again part of your reinforcement learning. Okay, so these are some of the algorithms I wanted to touch upon. Okay, and now we are about end of our first module, which I call it here. And here we'll talk about different challenges that we have in machine learning. Okay, so just let me take a sip of water here. So we'll talk about challenges like overfitting and underfitting. Okay, so overfitting and underfitting are two common problems in machine learning that can severely impact your model's ability to generalize, from the training data. Okay, so see, ultimate goal is that we learn from training data and then perform output on unseen data. That's the ultimate goal, right? So, if you get biased towards training data, okay, and then you won't be able to perform well on unseen data, right? That's the problem we're talking about. So these issues, overfitting and underfitting issues, okay, rise when model is either too complex or too simple, okay, leading to poor performance in both the cases. Okay, so what we want to have is that the modeling when you're doing, it should not be simple model, okay, on let's say small data set. It should not be a very complex model on too complex data set, right? Something in between or balance is what we prefer. But let's understand what each of these things mean. And then, of course, we'll see what is the best scenario situation. So when does overfitting occurs? Okay. So overfitting, okay. Now again, let's talk about a random example and then we'll come to machine learning. Overfitting is something, let's say, you are as a student, you've learned some concept, and now you want to prepare for, let's say, exam. Now, okay, so we'll take simple example. Let's say mathematics. Now, before exam, okay, you practice 1,000 mathematical sums. Okay, so 1,000 problems that you practice is like kind of coming across all kinds of problem. So now that you have practiced 1,000 problems of addition, and when you go to exam hall and and attempt, because you have solved 1,000 problems, right? Now, it's like you have kind of by hearted, right? Most of the question that you see in the exam would be repetition because you have done almost all kinds of problem, okay, with all possibilities of numbers, right? So the exam hall, you are seeing that it's same question that you have practiced before, right? And let's say 99, 98% of questions are same. So what happens since you have kind of by hearted, right? When you practice 1,000, right? If you practice 9 plus 6, okay, 100 times, okay, and then if somebody asks you in the sleep also, you will say 9 plus 6 is 15 because you have practiced so much, right? Now, so what is the problem with that? Problem with that is that you are not thinking. Okay, since you have learned so much, you have by hearted it so well that you are able to answer just like that. You're not even thinking. Now we want model to think, right? We want model to think because in reality, okay, it's not the same questions will come, right? In reality, they might ask something else. But if you are so by-hearted, so trained on this, the problem is we generally stop thinking, right? When we learn too much, right? That's what happens. We stop thinking because we know everything, right? So the problem with that is, okay, since you have by-hearted too much, okay, so overfitting, okay, is a similar scenario. Okay, so it occurs when model is too complex and captures not only the underlying patterns in the training data, but also the noise and random. Okay, so your answer is like on your fingertip. You are not thinking. You're not able to know the difference between noise and randomness. Okay, in the data set. Okay, so what happens as a result? You perform very well on the training data in the exam. When on the training data you perform very well because you have kind of by hearted everything. But when you are forced into the real world, what we call it unseen data in machine learning, then you start okay having problem because those numbers are not there and you are struggling to solve. So you are doing very well in the test, in the training, but you are not able to perform well in the real world. So, such models, okay, exhibits very high accuracy in training data set, but performs poorly on unseen data. Okay. These are your overfitted models that I'm talking about. So they're overly complex with a large number of parameters that allow them to fit the training data very closely, okay, including the noise. So here, if you see an example here in regression, let me see if I can have my pointer here. Okay. So this is your regression model. Okay. And this is the data set, right? Blue is the training data. So you want, okay, fit to be like this. This is the optimal fit. Okay. But you have been trained so much on this data set that you are capturing each and every movement. Okay. And the output model is result like this, not this. Okay. Now, when you put this model in the real world, if you put this overfitted model in the real world, it's going to fit like this. And data set, all the data set will not be like this. So your training data is accuracy is 100% and your test accuracy becomes very poor. So how do you identify there is a problem with your uh, if it's overfitting? So okay, so when you perform your training data, accuracy is like 100%, 99.99%. But when you do it on your test data, accuracy comes to 50%, 70%. There's a too much gap between your training accuracy and test accuracy. Your validation accuracy is poor, okay, and your so you have a high error, right? Poor, and your training accuracy is like almost no error. So this gap is too much. That's how you know that you have landed into overfitted scenarios. Right? So as I said, it could be because of model complexity, it could be because of insufficient training data, or you have too many features. Okay, you have included irrelevant features also in your analysis. Okay, so features which are actually not impacting the outcome is also impacting your process of developing this model. Okay, excessive training, you're training too much, with multiple parameters. Okay, so these could lead to overfitting scenarios. Then how do how do you manage it? Okay, so we use regularization, cross validation, where you break into multiple subset, like your k-fold cross validation techniques. Okay, we use pruning. Okay, so pruning, especially in the decision trees, it involves cutting back the tree by removing sections that provided little power in predicting target variables, right? So you don't end up building all possible combinations in tree. Okay, you remove the part of a tree which is not contributing much, right? So when you look at, you don't, okay, it will not be a complete decision tree to look at, but it will give you a better result. Okay, sometimes you might have to drop out some hidden layers when you're dealing with neural network. Okay, best thing is simplify the model. Okay, look at only fewer layers in neural network or fewer columns in machine learning. Okay, and increase the training data. You provide more data. Okay, in the training. That means you are not just by hearting the data. Okay, there's a different types of input data that goes into that. So that's your overfitting scenarios. Okay, which result into our carelessness, right? Okay. Now here also, same thing you can see in the classification also. Classification also, if you see, This is not a kind of model that we can generate, right? It is overfitted model. Now talking about underfitting. So underfitting scenario is when model is too simple to capture underlying patterns in the data. Okay, so as a result, your model performs poorly on both training data as well as test data or unseen data. Okay, so for example, okay, same example that we spoke about, right? Preparing for the exam, you solve only one or two problems. You don't solve thousand. You solve only one or two problems. So when you solve only one or two problems in mathematics, okay, what happens? You have not understood entire concept. So you will not be able to perform well on training data as well as your test. Okay, so you see here, both the errors are high. Okay, there's not much difference between validation and training, unlike your overfitted. Okay, so but training error is also very high. Okay, so both errors are high. You are not prepared. Basically, you are not prepared. You know, we talk about complexity in overfitting, here simplicity in underfitting. Okay, you don't have to, you can't be so simple also, right? You have to practice, right? So here, if you talk about the characteristics of your underfitting, we have low training accuracy. Okay, if you talk about bias, you have a high bias, right? And as I said, the model simplicity is one of the main cause of underfitting. You can have insufficient training. You have excluded or you're not included all the relevant features, right? Columns you are not taking. And the solution would be increase the model complexity. Okay, perform feature engineering to figure out which are the right number of features. Okay, don't be careless, right? It's like being careless. That okay. Okay, so try to look at your um, model and try to make it more complex. Whether it is about data set, it's about features. Okay, and if you do too complex, you end into overfitting scenario. If you leave it too simple, you're underfitting. Something in between is what we figure out. So see, if you look at this optimal fitting here, there will be gap between training and test, right? You will do well on training, you will not do so well on test, but the gap should be less. Here, there is no gap at all, and there is a too big gap, right? So optimal is where there is a slight gap between your optimal value. Okay. So what we say is, okay, and that's also our next topic, which is your bias variance trade-off. So, okay, the key to building a good model lies in finding the right balance between bias. Okay, so this is called bias. Okay, so error between your model error is called bias. Okay, so finding something where bias should be less. Okay, and then the variance. Variance is the difference between training and test, which happens in overfitting. Here, the variance is low. If you see, variance is low. Okay, the gap, but bias is high, right? Here, variance is high. Okay, and bias, okay, now with respect to training data is very low. Okay, with respect to validation is very high, but variance is the difference between them is very high. So you have to find the best. Okay, it cannot be zero, variance cannot be zero, and variance cannot be too high, right? Somewhere in between. Okay, this is what we call as bias variance trade-off. So bias variance trade-off is a can say fundamental concept, okay, in machine learning that describes the balance between two types of error, right? So what are those types of error? We have bias and variance. Okay, so what is bias? I just said bias refers to the error introduced by approximating a real world problem, right? So error between your model accuracy and the and the reality is like when you're able to make 100% prediction, right? 100% accurate prediction. Okay, so but if you talk about high bias, right? So a model with high bias makes strong assumption about the data, often oversimplifying the underlying relationship, right? So if you talk about an example, a linear regression model trying to fit a complex non-linear relationship, okay, which will likely have a high bias because it assumes linear relationship that does not exist, correct? So again, if you go back to previous case, okay, see, we have assumed a linear relationship, which is not the case in the data set. Okay, so your data set, okay, behaves differently. Okay, here you can see complex relationship, but we assume that it's a easier, okay, linear relationship, which will give you a high bias. Okay, so high bias causes underfitting, where model is too simple to capture patterns in the data. We have seen that. Now talking about variance, okay, so refers to the model sensitivity to fluctuation in the training data. Okay, so a model with high variance pays too much attention to the noise in the training, where you capture, every little, sorry, okay, the error, right? Where you're capturing even the noises. Okay, okay. So a model with high variance is overly complex, right? Adapts too closely to the training data. So as a result, what happens? It performs very well on the training data, but poorly on the unseen data. So what an example here, a decision tree with too many branches, right, is a overfitting. So what we do, we prune it, we remove the branches which are not relevant, right? So, okay, decision tree with too many branches can lead to overfitting and thus can lead to high variance. So what happens in the performance of the model? Okay, so high variance causes overfitting where the model is too complex. Okay, and okay, and also what we said is high accuracy on training. So the idea here is that we balance your bias and variance. Okay, so as you see here in the graph here, okay, as you make model more and more complex, okay, as you make model more and more complex, okay, your variance is increasing slightly. After a certain point, it will start increasing at a very faster rate. Okay, so now you know that this is overfitting side. Now what happens to your bias? Bias will start decreasing, right? When you train your model, it starts decreasing, error starts decreasing. After a certain point, again, it will go on decreasing only. Okay, so your bias doesn't, increase. It's keep on decreasing. So where you have, okay, just little bit high variance and low bias. This point is called your optimal balance. Okay, so here we are purposely, see what we are doing variance, we are purposely introducing error in the variance, right? We are purposely introducing error in the variance because we know, again, if you go back, if you have to see in this the previous here you see, okay, we want our training and test to be perfect. Okay, that means what you are doing in training, same thing you're getting in the test, right? So this is our ideal scenario where your variance, okay, variance is low, of course. You want bias also to be low, but that doesn't happen, right? If you try to increase the, if you try to decrease the bias, variance will increase. We want low variance, right? You want your training and test to be exactly same. It sometimes happen, right? When we train our data set, okay, with a certain model, oh, we get 90%, 80, 95%, 99% accuracy. But when you try it in a real world, okay, when you deploy the model or when you try with, the actual data which you would have got from, let's say, your research work, model is giving poor result, right? So we don't want that. We want exact same output what we got on training data should be reflected in our real data, but that doesn't happen. Okay, so we have to introduce variance, but to a certain level, not too high variance. This is what this graph is talking about. So we are introducing variance, okay, so that bias comes down. Okay, and where they are almost same, okay, this is your total error, because if you go beyond this point, your total error starts increasing again. Okay, so this is your underfitting side. Underfitting, you saw both the errors are high, right? Your training and test errors are high. Overfitting is where your training error is low, but your test error is high. This is your test error, sorry. And this is your variance. Variance is the difference between these two. So it is should be minimum as possible. Okay, not as minimum, sorry, optimal as possible, not minimum. Minimum would mean you are at underfitting scenario, right? So as optimal as possible, where total error is least. So key to building well-performing model is to find the right balance between your bias and variance. Okay, so a model with too much of bias, underfitting, too much of variance, overfitting, correct? Okay, so yeah, um, so okay, so these are problems. There's one more problem with the data set. Okay, okay, variance, bias, trade-off, right? Overfitting, underfitting, and there's one more problem with the data set, which is called as data imbalance. Okay, and you will come across this scenario, very often, right? Let's take a scenario where you are doing fraud analytics. Okay, you're working for a credit card company, and you want to predict, okay, every transaction you want to predict whether it is a fraud or not. So if you look at the number of transactions that are done, okay, every day versus the fraud transaction, right? In terms of percentage, right? The fraud transaction, okay, is very, very less. Okay, you might be doing 10 lakhs transaction and you might get only 2 or 3 fraud transaction. Correct? Now, if we build a model with exact same data, then what happens? Okay, you will come across a situation, okay, where the model say, oh, out of 10 lakh, only 10 are fraud. Okay, let me ignore this 10. Right? Okay, so model becomes biased. It says, okay, let me ignore this because even if I make 10 wrong predictions, 10 wrong out of 10 lakh is what? 0.001%, right? So accuracy is what? 99.999%. The accuracy is very high. So in such scenarios, accuracy doesn't matter. What matters is, are you able to capture the fraud transaction or not? So your accuracy could be even lower. You don't mind accuracy to be 80%. That means, many times we get a call. Did you make this transaction? Okay. It's okay to call a customer if the transaction is non-fraud. Okay. But if you miss to call a transaction, call customer on fraud transaction, it's a big pain, right? Even one fraud transaction would result into a lot of financial impact on both the bank or the customer, right? So it happens real world data, right? It's common to encounter situations where classes in a data set is not equally represented here, right? 10 lakh is no fraud and only 10 is fraud. Okay, so such scenarios, we generally call it as data imbalance. Okay, so before you build a model, you have to make sure the data is balanced. Okay, data is balanced. Otherwise, your model is going to be a biased model towards the majority class. Your model will assume that, okay, let's go with majority class. Let's, ignore no. So the model always will give you no fraud, no fraud, no fraud. Right? Okay. And this happens in many situations, right? If you talk about healthcare, right? Now, if you talk about the percentage of people getting a rare or very rare disease, right? We say, this disease is like 1 in a million, 1 in 10,000, 1 in 5,000. That means if 5,000 people go for a test, only one will get that rare disease, right? Now, how do you analyze such kind of data set? Very difficult to analyze. Okay, so as I said, problem with the imbalance is that it get biased towards majority class. It'll give you misleading information. Accuracy, you feel your accuracy is too high, 99.99, but that's misleading. Okay, it's not able to classify even one fraud, or in this case, rare disease or failure, right? So it gives us misleading accuracy. Okay, so what we need to do in such cases is we have to resample the data. Okay, so we need to resample the data. So we have two concepts here. We have something called as oversampling and undersampling. Oversampling is where you leave the minority class as it is. You take the minority class, one that has a less number of values, less number of rows. You create synthetic data. Okay, similar data you create and you bring this count up. Okay, so oversampling. So if you look at the here, if you see here, so this is our majority class, right? So many blue output and only few orange output. So what we do is we oversample. Okay, we create copies of this minority class so that now they are balanced. So we use technique like SMOTE, right? Synthetic minority oversampling technique. Okay, that is one example that we use for oversampling. In undersampling, what we do is we bring down the majority class to the lesser. So we leave minority class as it is, but we bring down the majority class. We undersample, we remove the sampling. Okay. So, but there is a risk here undersampling. Undersampling, okay, if you don't do it well, you don't know, you might be removing out important information, right? Important information can be lost here. So what we do is generally we perform combination of over and undersampling. Okay, so balanced approach might involve combination of both undersampling of the majority class and oversampling of the minority class to achieve a better balance without sacrificing too much of data, right? Something in between. And of course, anomaly detection, right? Fraud analytics is part of anomaly detection. It helps there. Um, 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 yeah, and a lot of this thing. Okay, what do you call the healthcare example, which I said. Also, you'll have data set like this. Okay, so in real world, you won't get perfect 50% data set, right? You will get, 90-10% kind of thing or 95-5%. Okay, so you need to use these techniques to build your metrics. Okay. So yeah, so with that, we come to end of our first part of our presentation, which was about understanding the machine learning, deep learning, the challenges, the problems. Okay. And now we will talk about the next topic, which is generative AI. Okay. So here focus is that we we talk about the latest trend in AI, which is generative AI, right? And so generative AI is what? It's about generating content. That's what we call generative. Okay, you are generating new content. Now this content could be your art, images, music, okay, designs, videos, right, text, right? So anything that you are generating new is called generative. Okay. So, next we have about, I don't know, 40 minutes or 50 minutes or so. We'll talk about, I think 40 minutes, right? So we'll talk about the technique, the ideas behind generative AI. So I'm sure, okay, most of you would have used ChatGPT, right? And ChatGPT can be used to create, lot of things, right? It can create long text. You can use it to create a story. You can use it to create poems, essays. You can use it to create language translation, ask questions. Okay, it can even answer you like a human being, correct? Like you can talk to ChatGPT like Q&A. It can evaluate your output content. A lot of things we can do with it, right? So the content that it generates is like it's like a real, right? It's very difficult to figure out the difference between whether it's a machine generated or human generated, right? And if we talk about the ChatGPT 4, it's even more improved over the ChatGPT 3 or 3.5. Okay, so now we'll talk about different levels, right? So AI is a bigger term, right? AI. Now these terms you'll hear in your daily life, right? So AI is bigger term. So what is the purpose of AI? Purpose of AI, okay, is to create human-like thing. Okay, now see, if I ask you what is the most expensive thing in the world, you'll talk about diamond, gold, right? Now diamond, we have artificial diamond, we have artificial gold. So if you can't afford to have a real diamond or real gold, you can buy artificial gold, right? Similarly, okay, the most expensive thing, okay, in my opinion, I think, and you will also agree to that, is human intelligence, right? Our brain, human intelligence. So if you can create artificial diamond, artificial gold, why not create artificial intelligence, right? So that we don't have to use our brain, right? We will use the artificially generated brain. So that's the whole idea, that can we mimic a human being? So now human being has two important roles, right? We perform two things, right? Most of us, like, first we think and then we act, right? So we talk about thinking and acting. So how does thinking come? Right now, if you compare yourself, now let's say you as a person today and you as a person 20 years back. Now, sometimes when we, look back 20 years back, what we did, we laugh at ourselves, right? Oh, I was so foolish. I did that when I was 20 years old. Because what happened now, like, at that point of time, okay, our learning, okay, our expertise was not what we have today. Today, we are much more matured. We have much more knowledge than what we had 20 years back. So, but 20 years back, it was we, who we are. So what happens, right? If you want to improve your thinking capability, right, you need to learn more. So what has happened in last 20 years? We have learned more, right? Now, it could be your supervised learning or unsupervised learning, but it is learning, right? You learn more. So machine learning is about learning so that you can make a better decision in AI, right? So that's why machine learning is a subset of AI. Now, deep learning is again a subset of machine learning, right? So here in deep learning, we're talking about algorithms or learning, which is neural based, right? Not like a probability based, but more of a neural based, right? It's even more better way of making decisions. Now, generative AI, generative artificial intelligence, or generative AI is a sub part of your deep learning. Okay, so it's even more better than deep learning. So it's a deep learning technique. That's why that's why we covered RNN, CNN. So it starts with CNN, which is your deep learning technique. Okay, you improve upon to RNN, which is again feedback based, right? Now we're talking about transformers, right? Which is part of your generative AI. Now, again, generative AI can be used to generate text, images, videos, and so on, right? So we're talking about, okay, generative AI, which can generate large language models. So we're talking about human language. Okay. Now, ChatGPT, okay, is good with English, right? Can generate English text. It is equally good to generate Hindi or Telugu or Malayalam text as well, right? So it is trained on multiple languages, and you can use it for different languages also. So that's the language model, right? We're coming down to language model. And then you have something called as generative pre-trained transformers. Okay, and we'll talk about it. One of the applications, okay, one of the way of doing GPT is GPT-4, okay, developed by OpenAI company, and ChatGPT is an application that uses GPT-4. Now, GPT-4 is company specific, right? Similarly, you have BERT and other models, right? Now, generative AI, generative pre-trained transformer, GPT is the concept, okay, of generating these large text. So this is the sequence. This is like superset and subset and things like that. And we are coming narrowing down to GPT. Okay. So this is about different models. Now there are three important generative AI techniques that generative AI is based on. Okay. So first we have variational autoencoders. Variational autoencoders are a type of generative model that uses neural networks to learn the underlying distribution of data, right? So they consist of an encoder that maps input data to a latent space. We'll talk about it, okay, in some time. And then latent space is then converted into your final output. Okay, and as you can see, it is generally used for creating images, anomaly detection, and data comprehension. Talking about GAN, GAN is again neural network, and it has two important players in it: a generator and a discriminator. Okay, and they play with each other. Okay, there's one more important difference between VAE and GAN is that VAE, okay, does not have any public data. Okay, whatever you give, that input is given into latent space, and this is then transformed into large output. GAN, okay, is you have generator and you have discriminator. This keeps on working, and then this also keeps on working in parallel. And there's a public data source which is also given as input to discriminator. Okay, and transformer is to identify the input text. Whatever input you give, okay, it tries to identify what input it is and then what should come after it, right? So attention is all you need, right? That's what we discussed. Okay, what, okay, you have certain word, now which word should come here? So you are comparing this word with multiple words and comparing the value, okay, score, and whichever has a higher score, this word you will place it here. That's in short. Okay, now let's discuss this in detail. Now, before I talk about you know VAE, I like to talk about these things in terms of story. So we'll create a story here, okay, and this story will tell us what VAE is all about. Okay, so let's take an example. Okay, so let's say, okay, once upon a time, okay, in a little village, okay, there lived a renowned artist known for creating the most beautiful and intricate designs or paintings. People from all over the world admired the artist's ability to capture the essence of the life in every brushstroke, right? But what happened? The artist was getting older, and the artist wished to pass on this craft to some young guy, right? So young, he was looking for an intern or apprentice whom he can pass his knowledge so that he could continue the legacy of this painter. Okay. So one day, a curious and let's say eager intern came to artist and asked to learn the art of painting. So artist agrees. He became happy that somebody has come to him to learn the art. But instead of teaching the apprentice, how to copy existing paintings, okay, okay. So he could have said that, okay, these are my paintings. Just start copying them, right? But if you start copying them, you won't be able to develop something better. So what this guy said, painter said, okay, he said to the intern that understand the essence of each painting, the deep structure, the meaning, the colors, why so and so color, why red, why pink, right? And different forms. And okay, so if he understands the idea behind this guy, right, how this guy thinks, okay, the painter thinks, why he chooses certain image, why he designs a particular way, how he chooses the color. Okay, if this intern is able to understand the idea behind the painting, then what will happen? This guy would be able to create different paintings, right, of equally good um, quality, right? And not just copies, isn't it? So what happens? The artist began by showing the apprentice, various paintings. Instead of focusing on every detail, the artist taught the apprentice how to observe the key features that made each painting unique. Things like composition, use of light, shadow, the balance of colors, and what this guy would do, would learn to encode these features, right? So this guy would encode these features into a simplified version of the painting. Just give me a second. Okay. So this guy would understand the concept, okay, of all these things that the painter was saying, the artist was saying, and he would learn the idea behind it. So once this intern mastered the art of encoding, the artist took that learning to a next step. So what the artist did was, he encouraged that guy to use these encoded sketches which he has captured in his mind to recreate the painting from scratch, right? But he was asked to add with his own, so capture those essence and add his own perspective to it, right? So at first, what happened? Of course, he would struggle, right? The guy would not become expert in first attempt. But when he kept on trying and trying and trying, he started giving better result, isn't it? Okay, and then this guy said, okay, now it's time for you to create a painting that I have never shown you before, right? The artist has never shown him before. Okay, and then what happened? Okay, artist would recreate a new painting which would have been as good as this artist painting. Okay, that's the variational. Okay, first it was autoencoder. I show you image, you capture, you learn the concept behind it, and then you reproduce it. Okay, now it's saying, okay, you have learned it. Now don't reproduce it. You create your own painting. So it's not Xerox, it's not copying. It's about adding its own variation. So we call it as a variational autoencoder, or VA in short. So autoencoder is a concept, okay, where you have input, okay, which is called as encoder. So autoencoder has encoder, you have decoder, and you provide the input, right? You provide, mostly it is used for image, okay, improving image quality. Okay, so here you have concept like mu, your mean, mu, and standard deviation. So it captures the input data, whatever you give, text or image or videos, whatever. Okay, and this is your embedding. And when this is given, okay, this ultimately it has to come as a number only, right? Whatever data you give. Now this data is encoded. Okay. Now this encoding, you see, there is the image designed such a way, right? So this when this intern looked at those paintings, right, he did not remember the entire painting in his brain. He captured the important essence, right? If this is what it should be, you should use this kind of color, right? That essence is what is captured here. Now this essence will be a very small piece, which is called as latent space. Okay, so you have this input, you capture this input, and then you convert into a latent space, which is a much lower dimension than this, right? This is a very high dimension, and it is not transformed into a much lower dimension. Okay, it's a lower dimensional representation of the input. Now, this is the idea that you have in your brain, the essence that he captured. This is the essence. Okay, in a short, you don't capture the entire image, but you capture the essence. Okay, so the latent space is where that encoded information is living, right? Next, what happens is you decode. When he was asked to reproduce it, the essence that he captured is now again explodes into a much bigger dimension, right? So you create a simple you create a sample output, you create a, what you call a reconstruction is done from latent space to your, to your decoder. So this is the job of decoder. Encoder, latent space, decoder. Now, if the image that you are trying to, perform is, let's say this is the image, right? And if this exact same image is done, this is what autoencoder would do. Okay, you take the input and you produce the output. But there's a difference here. What is difference here? Difference is there's a variation that is added. Now, variation is based on what you have learned here. Now, this intern that is working with this artist, okay, has not learned painting somewhere else. Okay, the guy has learned working with this, with this artist itself. So what is happening? Okay, learned all the concept by looking at the painting and is able to design, okay, painting. Now this is not going to be exactly the same, right? So generally when you have a old image, okay, which is, let's say, low resolution image or black and white image. So you can create same image with, let's say, high resolution or color. That is the variation. So variation is only based on some limited thing, okay, where you can increase the pixel, right? So you see the image, you capture it into a, latent vector or, okay, your, this, what do you call, the latent space or latent vector, you capture into lower dimensional latent vector, and then you explode it, reconstruct it, okay, as a image. So you can make it more, add your own variation, right? You can make it more, with higher pixel, or you can add colors to it. Okay. So this is how your VAE works. Mostly, okay, you would have known that it is used for images, but you can use it for creating, um, anomaly detection and semi supervised learning tasks where you learn 90%, 80% of the stuff, but you add 10, 20% of variation to create a new one. So your variational autoencoders are models capable of learning to both reconstruct and generate new samples from a given data set. By what? By mapping the data into a continuous latent space. So this latent space allows for smooth and continuous representation of the data, enabling the generation of varied samples with seamless transitions, right? From one form to another, right? So examples I've already given you, image generation or anomaly detection. So this is one important framework or model which our generative AI uses, okay, to generate images or videos. The next one we're going to talk about is called, okay, generative adversarial network or GAN. Okay. Now again, I'll tell you a story and we will compare this with a story. So let's say there are two talented bakers in a town. We'll call them a Ginny and Andy, let's say. Okay. Now, Jenny is a master at baking delicious cakes, and Andy is a, let's say, expert at tasting and spotting, each qualities of cake, right? If the quality of cake is good or not, if it is not good, what should be improved and things like that. And Jenny loved to make cakes, and let's say Jenny wants to become best baker in the world, right? Jenny wants to become best baker in the world, and Andy has a very sharp tongue, right? As I said, it can figure out what is wrong with it. So now Jenny thinks, okay, that if I want to become a better baker in the world, I need someone who would help me to improve my techniques, isn't it? So Jenny goes to Andy, says that, okay, I want to become the best baker in the world. Can you please help me? So whenever I bake a cake, can you tell me what's wrong with my cake? Okay, I said, okay, we'll play that game. Okay, so they decided to play this game that every day Ginny would get a new cake and Andy would taste it and will tell it if it is the best cake or not, right? If it is not, why it is. Okay, sometimes it might say that it is too salty or it is too dry or whatever, right? But then, okay, uh, uh, as a as Ginny would also want to know if Andy is giving correct feedback or not, right? So what Jenny would do is one day might get her own cake, or it might get real cake from somebody, or the best baker, the best baker in the town, right? Just to make sure that, and it could test Andy also if Andy is doing job or not. Okay, so what happens? Okay, every day Ginny would get a cake, and Andy would taste it and say that, okay, your taste, your taste is good, or so this is the wrong problem with it. So what will happen after a few days? Ginny will be able to make a better cake, right? So what happened here? Ginny is like a generator. Okay. So generator in GAN. So GAN is made up of two words, generator and discriminator. Generator's job is to create new content. Okay, so just like generator, Genie is able to create better and better cakes. Okay, until what? Until it is difficult or it is not possible to differentiate between Genie's cake to the best cake in the world, right? When Genie would get the best cake in the world, then discriminator or Andy here would not be able to, be able to give any feedback for improvement. Okay. Andy will say, okay, this is the best cake. Now, in that way, your Andy is acting like discriminator. Okay. So this one's job is to tell if the cake is real. Well, now here we're talking about cake, but in generative AI, it is about the data. Okay. So Andy will say if the data is real or not, right? So what has happened here? Okay, what happened here? So you have generator, which is creating new and new and new content every time. Okay, and discriminator is also in parallel, it's working and will evaluate the output. Okay, and as long as discriminator has some feedback to the generator, it is not shown to the user. After practice, what happens? And by the way, both are improving their knowledge, right? The generator is improving based on what discriminator is saying, and discriminator is also trying to figure out, how can I find a mistake in this output, right? So initially, it may be easy for discriminator to find a mistake, but as generator is improving, discriminator also has to improve to find the mistake, right? So generator is producing new content, discriminator is is trying to fine tune the output, and then finally, okay, after many iteration, what happens? Okay, discriminator would not be able to differentiate between fake and the real one. Okay, and the objective of GAN or your generative adversarial network is to reach that level where discriminator is not able to find difference between fake one and the real one. And with generator, when it's creating the fake images, is passed as real and given to customer. Okay, so when we look at text, or for that matter, again, this is used for images and mostly for videos we use GAN. Okay, and they'll tell you there's one difference between GAN and this thing, VAE, which is here. So in this case also, if you see, you have a generative network, okay, which is very much like the encoder, right? It gives, you give the input to it, and that input is based on that input, it creates multiple fake images or videos. Discriminator will say this is not, this is fake, this is fake, this is fake. Now it says, oh, it's real. And that is passed as a real one. Now here, okay, how does discriminator learn? Okay, now see, not anybody can find mistake with Jenny's cake, right? A baker can only find mistake with Jenny's cake. Somebody who understands baking process, right? So your discriminator is learning from the real images. So you need to pass real images also to the discriminator. Okay, so here what happens? Okay, so let's take this example. So you have generator here and you have discriminator here, right? Now you are passing, images or videos for that matter. Okay, now the job of discriminator is to create new images, of course. But you see here, this image, this lady is looking to the side, right? But her face is turned. Okay, this much variation is not possible in variation autoencoder, but this much variation is possible in GAN because GAN has got this public data. Now you see, okay, these are the real images. So this is how a person is looking to the left, and this is the same person looking forward, front. Okay, side, front, side, front, side, front. So discriminator is learning from real images that we are providing. So now it knows that, okay, this is how, a side pose would look like. So the learning that it has done, based on that, it is trying to predict your frontalized output. Okay, so here it is learning based on the generator, but how will it know that you are generating a real image, not fake one? You're generating a real video, not a fake one. Okay, so discriminator will learn from real data and then calculate accuracy on the generated data by generator. Okay, and one fine image, discriminator will okay, saying yes, this image is the output image is of front view of this input image. Okay, now in VAE, you could add better pixel, you can add colors to it, but you can't change the entire dimension of the image. But here you can change the entire dimension. As I said, it is mostly used for creating videos out of images, or you're creating a new videos altogether. Deepfakes. okay, uses GAN. Okay, we talk about deepfakes, right? GAN uses deepfakes. Okay, so your generative adversarial network GANs are I would say versatile tool that can be applied across various fields for creating high realistic data. Okay, even when available data is scarce. Okay, you don't have enough input data to generate output, but it has access to the public data. So when you talk about medicine and material science, your GANs can generate new examples for image data sets, making it easier to conduct research with limited data. The synthetic data that we talk about. Okay, in creativity industry, GANs can create cartoon characters, scenarios, your video games, your videos, okay, which is difficult to, let's say, even shoot, right? It can create those videos. Photographers and videographers can use GANs to produce your realistic, photographs, and it could use different poses and things like that. But all these are good as if you are doing it for good purpose. But you can also create deep fake videos, right? You can create fake audios, right? You learn from the audio samples. You create a different text but same audio sample, right? Can lead to problems. That's the GAN for you. Now the VAE, right? I told you we'll be discussing transformers. Okay, not VAE, sorry, the transformers. And we're discussing transformer again. So we started with a little bit of transformer. We said that, what transformer is, putting the right words in the place. Okay, now let's talk about, we'll understand transformer using a story. Okay, so let's say there's a, um, okay, so let's say, I'm just thinking, okay, let's say there's a village, okay, and in village they started digging, new site. So what these historians, got was old site with different text. Now, okay, when they got those data text, right, the text that was there written on those bricks or whatever walls were not the language that people spoke in that village, right? It's some very old language. It was spoken 5,000 years back, 10,000 years back. Now, how can you decode that language? You can't decode that language. How do we decode that language? Okay. So how do you decode? Sorry, those kids. So how do you, okay, decode the language which people never spoke, right? So there was a old guy, old wise guy, okay. So what he did was, okay, he would look at the each word and look at the positions of each word, correct? And he studied the position, okay, and how the sentence was constructed, okay. So based on, each sentence, okay, he would look at the association of different words. Okay. Now, when you look at this different words, their position, how they are used, it could decode the language. Right? Now, even though this is something totally new language, but based on the position of different words, how these words came along together, okay, we could decode it. Okay. So it gives you power to decode a language which is not understood or never seen before. Okay, this is what we call as power of parallel reading. You read multiple text. You read each word in multiple text, multiple lines. Okay, and using what? You could translate one language to another. You could write a story or poems, right? You could even generate languages which were forgotten, nobody knows, right? So what did we learn here? Okay, so transformer, okay, is of course, a powerful tool, okay, and just by learning the words and its position, the relative position between different words in a sentence, you will be able to create or understand new content or create a new content or understand the existing content. Okay, So what do we have here? So here, let's say you are giving an input. Okay. Now each of these words are going through an encoder. Okay. So this is not a, it goes through multiple layers of encoding. First of all, you need to first understand the words. Okay. You need to first understand, okay, each of the individual words. What are you doing? Then you understand the concept, okay, of each word. Okay. Then you look at the relative position. So maybe initially you might start with 0 for what, 1, 2, 3 as encoding, but at every step, okay, these values would change. Sometimes, okay, let's say, for example, what are you doing is one way, right? You can also say, um, let's say, I'm just trying to, replace the word. Can you replace this word and form a sentence? What are you doing? Are you, okay, so let's see this, okay? Are you doing what? Now, are you doing what? Okay. Are you doing? Now, if I look at are you doing, are you will have a stronger, correlation between them in the sense they can be used together. You doing can also be used together. But will doing and what, something is wrong here. So the relationship when you encode it, okay, doing what, okay, will not be good way to put this word together, right? Okay. Then you try to do, okay, are what you doing. Okay, then again, because this is what you know, input data, right? Then you are trying to figure out, you're trying to learn from the data language that you know. Okay, so you know that, okay, what should come in the beginning only, what should not change. Okay, so you fix the what. Now, what with are, what with you, what we doing, what doing are you? Probably no, right? What you doing are, you are, what you are doing probably looks better. So it tries to find, okay, each of these encoder will create a new set of values. And after doing, all these encoding, okay, finally you might come up with 0.22 minus zero point 0.8, something like that, which indicates the position of these words. Now you start decoding. Okay, now it could be a simple decoder within one line, or you have to go through 2 layers or 3 layers or 4 layers. Okay, and finally the output that you get would be a related output. Okay, so here again you have encoder and you have decoder. Encoder looks at feed forward and self-attention. There is no feedback, but here there is a feedback. Okay, so your feed forward, encoder, decoder, attention, and self-attention. So this is the part of your decoder. Okay, and this is how transformer. Okay, so maybe, one day we can just focus on transformer, trying to understand, how transformer works, and here into do a lot of other things that happens here, like there's one simple embedding, then chunkings and tokenizing. All those things are part of each of these encoder, and then reverse they have to do it again. Okay, so okay, again you have to do tokenizing first, then chunking, then embedding. Okay, the reverse process. Okay, what we have done here, it should happen in the reverse process here, and then finally you get an output. So this is your transformer. Okay, at a high level, what it does. So you have encoder, which has a stack of layers that process the input, right? These are the stack of layer, and then decoder, which has again a stack of layer that generates the output sentence, right? And here you talk about input representation, self-attention, attention score. Okay, this is what we calculated, the attention score. Okay, what else? Yeah, we talk about feed forward here, right? So feed forward neural network is to, which further processes your combined information. Okay, after going through all these information, and same thing will happen. Okay, in reverse order. Okay, in decoder, right? And of course, with the prompt engineering, and this is like key the role that we have and key application of your transformer. Okay. So with that, we come to end of Gen AI. Now we just talk about, benefits. We all know we can create automative creative tasks. The content creation is faster and you're getting a personalized experience, right? With generative AI. And you have challenges like bias in AI. You have who owns it, right? That's a big challenge, right? Well, if I generate a content using ChatGPT, who owns the who owns it? Okay, can I claim it as my own, right? So these are some of the challenge, and of course, you will see a lot of job role being displaced, right? Replaced with newer roles. So these are some of the ethical challenges with Gen AI. So with that, I stop my presentation